Okay, good evening to all of you. It's a pleasure to welcome Professor Manoharan to speak to us on space weather this evening. Professor Manoharan was in the Tata Institute of Fundamental Research, where he was my colleague for decades together. And during that period, he was instrumental in developing monitoring space weather via interplanetary scintillations using the UT radio telescope, which had yielded a lot of very interesting results on space weather. And currently, he is at the Arecibo Observatory. He's a senior research scientist at the Astronomy Department of Arecibo Observatory. As you'll know, Arecibo Observatory had an accident last year. We're thinking of new plans to revive Arecibo. And he's attached to the University of Central Florida, which now manages the Arecibo Observatory. So welcome, Professor Manoharan, and thank you very much for taking the time to speak to us this evening on space weather. Thanks.
Oh, thank you very much, Sykes. Good evening to all. I'm happy to be with you this evening. We will discuss some aspects of space weather, and we will also discuss some of the radio astronomical tool helpful in studying space weather events as well as space weather applications, actually. So, okay, I would like to thank Sykes and all the organizers for giving me this opportunity. Okay, so my outline of my talk. Okay, we'll see some briefing about space weather, and then we'll see the solar radio astronomy and its importance in understanding sun and space weather. So that we will spend some time on that. And then radio interplanetary scintillation technique, actually, because I've been using interplanetary scintillation technique at UT radio telescope for a couple of decades to study quiet solar wind as well as transients coming from sun to earth. And then so we will see the remote sensing of the three-dimensional heliosphere and the tracking coronal mass ejection in the three-dimensional space, actually. So we'll see. And also UT radio telescope sensitivity as well as the UT radio telescope itself was useful to observe some more than 1,000 radio sources per day on interplanetary scintillation mode. So we could reconstruct the heliosphere from something like 1 to 3 hours time period. So we will see that some of the results of that there. So okay, to start with, okay, let us see space weather. Space weather describes condition in space that affect the Earth, near Earth environment. It's a consequence of the behavior of the sun. Sun is active, it's not steady, it's constantly changing. And then the solar wind blowing out of the sun's atmosphere that shapes the Earth manosphere. The Earth manosphere gets the shape because of the solar wind pressure, and then the solar wind it helps, or it fills the entire solar system or the heliosphere. It's a heliosphere is like a bubble, plasma, magnetized plasma bubble in the interstellar medium, actually. So the space weather, the main part of space weather is the suns and its activity. And also the space weather depends on the nature of the Earth's magnetic field. When this space weather even reconnects with Earth's magnetic field, so it can have a depending upon the magnetic field orientation and depending on the magnetic field strength, the space weather even can vary. So it depends on the Earth's magnetic field and it's our location in the solar system with respect to the sun, how we are located. For example, space weather effects at the Earth and the space weather effect in Mercury or far off planets, it can be different actually. Okay, so the space weather effects depends on the location of the planetary system, planets at the with respect to the sun. Space weather studies, okay, it requires both ground-based and space-based observations. Okay, so so, for example, if you consider solar influences on the Earth, starting from the core, solar dynamo, and then energy output, solar energy output from the sun as a solar wind or radiation or particle acceleration. So the radiation has a effect, direct effect on climates, and then in the troposphere, ozone layer, and the mesosphere, lower thermosphere, and upper thermosphere, and ionosphere. So the radiation has effect, okay, solar radiation, okay, whether it's a UV, visible, infrared, and radio. So they have effects, okay. And also the energetic particle also, like high energy proton, they have various effects at various layers on the Earth's atmosphere. And then the particle like solar wind, and then the magnetic field coming out of the sun, which forms the interplanetary magnetic field. So they merge or they interact with the Earth magnetosphere, and then they try to pump energetic particle. So this gives a overview of how the solar effects or solar activity can influence the near Earth environment actually. So space weather science application includes this is the relation between sun and the Earth actually. So sun and Earth connection is studied in several aspects actually. Okay. So this actually, I'm sorry, this is not a very clear view graph actually. So space weather, like coronal mass ejection, the high speed ejection coming out of the sun with the magnetic field and mass, they can affect the satellite operation. Sometimes they affect sensitive electronics in the satellite, and then GPS communication, and then human in the space, like international space station and things like that. And then the geomagnetic effects caused by space weather events can cause stray currents, which can affect long pipelines actually. Okay, so that's the one space. And then power grid, the currents in the ionosphere can affect the can blow off a transformer, so power grids also can get affected. And then the polar region, our magnetic field, magnetosphere production is not very strong actually. It's very weak in the polar region. So the solar wind getting pumped through polar region can affect aircraft communication when we take high latitude flights. And then so on the water supply can affect it because of the power and other things. So this gives some aspects of space weather actually. Okay, so in India, space weather research is being conducted at various institutions. So this chart gives the institutions involved in space weather studies actually. So some 5 years back we wrote a paper actually. Okay, so this Bhardwaj et al. Paper, this appeared in the Space Weather Journal. If you have chance, you can read this paper. This paper summarizes the Indian perspective of space weather actually. So in the science department, Department of Science, CSIR, and the Department of Atomic Energy, DOS, Department of Space. So under this, several institutions are there, like IIG, ARIS, IAA, and CSIR, NPL, NGR, and then DAE. Okay, we have at TIFR, some of the colleagues, they are doing solar physics research as well as in NCRA, and REC UT was doing a lot of space weather related studies. And then DOS, NARL, PRL, and then their supporting field stations or observatory. The academic institution, UGC, HRD, and IASA, and then along with that, all the universities are participating in space weather actually. In India, solar, interplanetary, and manosphere and upper atmospheric measurements and observations from ground and space-based observation are employed to study various aspects of space weather, such as modeling of the solar modeling, solar dynamo, energy particle eruption process, like studying flares and coronal mass ejection, and dynamics of low latitude ionosphere, thermosphere, and plasma instability in atmosphere. So in India, we have a large range of space weather studies, and then institution and universities involved in space weather studies actually, and also our latitude starting from the south tip to north tip, we have a large latitudinal coverage. So a lot of instruments operate in the geographic latitude range, as well as in the east to west. We have good longitudinal coverage also. So this gives the institutions and universities involved in space weather studies actually. Okay. So we are also planning India's solar mission actually, Aditya L1. Okay, so for example, NASA and European Space Agency, JAXA, Japanese Space Agency, they are operating multiple space missions for exploring solar activities and characterizing the space weather. So India's first solar mission, Aditya L1, has been conceived as a 4 kg class satellite, and it will be launched in the 8-kilometer low Earth orbit. And also it has several instruments like coronagraph and ultraviolet imaging, and then particle experiment, plasma analyzer, and then X-ray spectrometer and manometer. So this spacecraft has a range of science instruments, and then one can see the details of the Aditya L1 at ISRO website actually. So when it is getting, because most probably it may get launched close to the, this gives the solar cycle close to the coming solar maximum. So we will have a great chance to do research on near sun effect of space weather events to up to near Earth environment. So Aditya L1 will give a good chance for us to do space weather studies actually. Okay, let us see solar radio astronomy and space weather. As we said, the sun continuously changing in all time scale. The solar activity arises or comes because of the magnetic field interaction, the plasma and magnetic field interaction that leads to the solar activity. Solar radio emissions are a signature of complex thermal as well as non-thermal process actually. So some of the processes can be explained by the temperatures. Some of the processes cannot be explained by the temperature, so we call them as non-thermal, occurring in different levels in the chromosphere as well as in the corona and in the interplanetary medium. So and then the mechanism involved are free emission, okay, free electron emission, Bremsstrahlung, and gyrosynchrotron emission, and plasma emission, and the gyro resonant emission, possibly by heating. So various mechanisms are involved in producing radio emission. Okay, so the radio emission intensity can be a slight increase compared to the, because sun itself has a quiet sun radiation. So it can be slight increase above the quiet sun, or it can be several orders of magnitude increase in short time scale, actually within some less than a second to within few seconds. So the brightening can increase. So solar radio emission gives a very good diagnosis of the space weather events, as well as the activity taking place on the sun. Some of the specific radio events, okay, are associated with the transient solar eruption, like type 3 radio burst. You might have heard in the radio sun lecture about the various emissions. Okay. We will also see briefly, but some of the type 2 burst, which is a measure of shock waves propagating in the corona. So those associated events, they have direct consequences in the to the geomagnetic effects, actually. So to understand geomagnetic effects, some of the radio events are important, and they are studied in detail, actually. Okay. But the sun is one of the strongest radio sources in the sky. So you see a image of the sun at 4.6 gigahertz, imaged by VLA. So it's sun radio flux, actually, or radio flux density increases with frequency also. Okay, you might have heard of all those things. But sun is very strong, and also when the activity or when the transient take place on the sun, like during solar flare or coronal mass ejection, the intensity of radio emission can be thousands or several orders of magnitude higher than the background, actually. For example, here we see various solar burst, type 3 burst, actually, caused by relativistic electrons beaming, and then the slow drifting burst, this fundamental and the harmonics. Okay, they give the shock wave propagation, and then the continuum emission, the mass moving out of the sun, they cause type 4 or continuum emission, actually. So this type of burst at in high temporal as well as frequency resolution, they are required to study, actually. For example, ground-based multi-frequency radio measurements provide diagnosis of eruption, magnetic field structure, and density. For example, in this plot, so here we go from the close to the sun or close to the photosphere to away from the photosphere. So if you go to 1 megahertz or some few kilohertz observations, actually, so even at low frequency, the radio observations are made from space, like wind wave spacecraft or stereo and Ulysses. They had a low frequency radio instrument, so they could probe far away from the sun. So close to the sun, as we go lower and lower frequency, we go far away from the sun. So we probe high density region to low density region, as well as the magnetic field configuration, because these events are associated with open field configuration. Okay, so for example, so they give information about eruption, magnetic field structure, and density variation with the height and low frequency below 15 megahertz. Ionosphere can attenuate the low frequency signal. So we need to go to space to observe low frequency, like wind waves, stereo waves, Ulysses Europe. So these instruments gives a low frequency observation. So low frequency radio observations are also very important in understanding space weather event, actually. So this cartoon gives this is by Dale Gary. This gives the during a flare what kind of magnetic field configuration incidents. So in the closed magnetic field configuration, in two polarity region, hard X-ray dominates, actually, and then the loop top soft X-ray, and then above the loop top microwave emission, and then in the ejection site or in the magnetic field reconnection site, particle acceleration is enormous. So the reconnection, what is the scale of the scale size of the reconnection, or what is the typical size of the reconnection? These are all the open questions. Still, we are not able to answer such questions. So in the particle acceleration, how thin is the magnetic reconnection site? So that's also a open question. And then what causes the difference in acceleration? In some reconnection site, we get low energetic particle. In some reconnection site, we get very high energetic proton. What is the cause for such differences actually? So the reconnection, understanding reconnection site radio plays a major role actually, and also there are a lot of theories and experiment and then because, for example, I have done so much work in flare and CME initiation using radio, X-ray, and optical observation. But we gave a size of the reconnection something like less than something like 100 kilometer and things like that, but that's not sufficient. We need to though. So how the mass ejection speed varies as a function of rate of reconnection. All these things are actually, so in this region, okay, 2 to 1 gigahertz emission is important to understand. In this region, the downward moving particle, so the particle moving from low density to high density, they cause a reverse burst actually. Normally the burst will be traveling from higher density to lower density, so we get forward moving burst. Okay, so this cartoon gives the how important important is the radio observations actually, along with, because solar physics, maybe that's true for other astronomical studies also. Now we need multi-frequency or multi-wavelength study, starting from small wavelength to large wavelength. So in understanding solar activity and solar eruption, radio observations play a major role actually. So again, this contour. So when this mass is released, we get typo continuum. Okay, so the structure of the typo continuum gives the ejected mass as well as the magnetic field actually. So okay, this another cartoon. This gives the radio emission layers actually, 5 gigahertz, 8 gigahertz, and 11 gigahertz. So the 5 gigahertz is at the top actually. So the 8 gigahertz is just below the 5 gigahertz layer, and then 11 gigahertz, that's below the 8 gigahertz layer. So that gives some kind of radio carpet actually. As we go lower and lower frequency, we see carpet moving upward above the solar atmosphere. So this is an example actually to show. So these lines are magnetic field lines, how they are connected at different parts of the sun actually. So so on top of the optical layer, how the emission layers are located. So this cartoon gives that. It's an example actually. So the another thing is the type 3 actually, the fast drifting electron beam. Pardon?
Hello.
Hello.
Sorry, sir. Sir, I'm Akash Kulkarni. I had a question for you.
Okay. Yeah, please.
So regarding the previous slide.
Okay.
Sir, there you are mentioning that you have layers of emission. I didn't understand, like, how do you map to a particular surface as this is a surface is giving me that radiation?
Because see, the radio emission depends on the radio emission depends on the density actually. So the density frequency, they have a relation actually. Frequency is related to square root of density actually. Okay, so that it requires some density model also. Yes, yeah, okay, yeah. And also again here, the see close to the sun, we have a high density plasma. As we go away from the sun, the for a typically spherically symmetric expansion, the density can go as 1/r square actually. Okay, so but the electron beam, they follow the magnetic field line. So these are all the interplanetary magnetic, because of the sun's rotation. As the sun is rotating, the frozen in field lines are dragged actually. So the curvature of the dragged field lines depends on the solar wind flow. If the solar wind flow is very high, let us say one eruption is coming out of the sun, it's moving at about something like 3000 kilometers per second. So then these field lines will be going straight actually. So these field lines are typically for 300 to 400 kilometers per second speed. So this curvature. So the electron beams, they follow the magnetic field. So by probing the interplanetary plasma at high frequency, at very low frequency, you can track the or trace the type 3 burst. So, for example, this work was done using the Ulysses spacecraft radio measurements actually. That gave the shape of the Archimedean or Parker spiral actually. So this is another example actually, as we move out of the sun, how the magnetic field orientation and then the type 3 burst following the magnetic field orientation actually. Yeah. Okay, so for example, solar radio astronomy and space weather, how it's linked. For example, NOAA, they operate a solar space weather monitoring center as well as prediction center actually. So space weather prediction, the SWPC we call it. So they issue alert following radio events observed actually. For example, at 245 megahertz, radio burst with peak flux greater than 100 solar flux unit actually. Solar flux unit is 10 to the power of 4 Jansky actually. Okay, so 10,000 Jansky. So if any observation with at 245 minutes observed with this flux density, so they issue a warning actually. And then similarly Nystrom, okay, and then 10.7 centimeter, that is the 2.8 gigahertz flux. If it is greater than 100% of the background solar flux, they issue a warning. Any type 2 event is observed, or any type 4 event is type 2 event represents the shock wave. Type 4 event represents the moving plasmoid actually. So they issue actually. So the real-time detection of solar radio emission at a different wavelength with a high time as well as frequency resolution is important for space weather diagnosis. For example, this warning issued on 28th, day for yesterday by NOAA actually. You can see, for example, there was a M-class flare. It is an X-ray flare, and then the 245 megahertz flux density was a 160 solar flux unit. So they issued the warning, and then this is continuum. This is type 4 event. There's another type 4 event. The type 4 event was in the frequency range of 114 to 180 megahertz. Okay, so they give, and then this is the fixed frequency. 245 minutes, it's 120. So like this, they issue warning. Actually, this is I just while preparing the talk, I pulled out from the NOAA Prediction Center. So actually, the radio observations are essentially required to issue the space weather warning. So the radio observations are important in understanding the space weather. Actually, that's the. So this plot gives the horizontal axis year, and then vertical axis solar flux unit. So the plot goes from 245 megahertz to something like 1500 megahertz. So you can see as a given time, the background solar wind flux density increases with the frequency, actually. Okay. So, and also all these variations, for example, in the 1500 megahertz, you can see a lot of variation. So during solar maximum, this is a solar maximum, again, another maximum. This is a solar minimum period. During solar maximum, the variation in flux density or variation due to activity of the sun is high. Actually, here also one can see that actually in two solar maximum, you see, whereas during solar minimum, the variation is within limited range, actually. Okay. So this gives a typical effect of solar activity in radio emission coming out of the sun. Okay. So this plot gives the because 10.7 centimeter flux nicely correlate with sunspot activity. So the horizontal activity is the sunspot number. This is the 10.7 flux. So this actually 10.7 centimeter radio flux is used as a proxy for solar activity. So that's the proxy, and it has been modeled. A lot of researchers, they are working on this, actually. So this has a very nice correlation, actually. And also here we see this horizontal axis again year. And then this is number of geomagnetic activity. So intensity less than 100 nanotesla, actually. So this is a DST index. So the index close to zero is no activity. As activity increases, -10, -50, -100, -400. So they indicate the strong magnetic activity. For example, -100 nanotesla is assigned as as intense. -200 is most intense. For example, in the 1989, there was a space weather activity which affected the power grid in Canada. That was something like -300 or -350. It's okay. And then there was in 1859, I think 1859, Bombay Colaba recorded geomagnetic storm, which was close to something like -1000, actually. So that event was a very strong event. It caused telegraphic line failure throughout United States and things like that. So one can see as the activity increases, the geomagnetic storm activity also increases. So as we see in this plot, actually, here we see large number of geomagnetic activity, and here also large compared to this quiet region, actually. Okay, that's it. Okay, coronal mass ejection. Okay, then now let us turn our attention to how to track coronal mass. Coronal mass ejection, they are largest phenomena associated with the dissipation of magnetic flux at and above the surface of the sun. So the speed of ejection can be something like a few tens of kilometers to few thousands of kilometers per second. Each coronal mass ejection involves ejection of magnetic field as well as mass in the range something like 10 to the power of 15 gram actually. So they carry huge mass as well as magnetic field from the sun. And then during solar maximum, the number of ejection can be large compared to the number of ejection during the solar minimum. The earth-directed CMEs are responsible for most of the intense magnetic storms at the Earth. So that's important. So the CME pushed towards the Earth, the CME moving along the Sun-Earth line, they can be hazardous. Okay, they can interact with the Earth's magnetic field. They can cause intense geomagnetic storm actually. So there's a large number of researchers. They are studying Earth-directed CMEs when they hit the Earth. What is the relation with respect to the CME size, speed, and the magnetic field associated with the CME that's being studied actually. So since CME can erupt in any part of the sun, three-dimensional view of CME is important. Interplanetary scintillation technique is useful to track CME in the sun-Earth distance as well as in the to view the CME's propagation in the three-dimensional view. So if we can observe large number of interplanetary scintillation source, one can get an idea about the CME structure actually. So this the background move is taken by SOHO spacecraft by a LASCO coronagraph, which is sitting at the L1 point actually. So this is the occulting disk. This is the solar disk. So the solar disk is covered with occulting disk to suppress the brightness coming from the sun, so one can see the brightness of the CME. Because so one can see the magnetic field configuration associated with the CME also. So understanding propagation and eruption of CME, even one required solar interplanetary medium measurements as well as model actually. On the disk we need a photospheric and H alpha observation, and then source region X-ray, UV, and then in the initial stage one need a coronagraph, interplanetary scintillation, and the radio measurements. And then understanding the expansion and the propagation models are used. So the space weather event understanding from sun to earth, it requires various types of measurements actually. Okay, from optical and the X-ray, UV to radio and white light coronagraph measurements are mostly white light measurements, and as well as modeling actually. Okay, so let us see how we'll take interplanetary scintillation. Okay, it exploits scattering of radiation from point-like radio sources, example quasars and radio galaxies of size less than 0.4 arcsecond or 400 milliarcsecond by small-scale density irregularities in the sun actually. Okay, sorry, in the solar wind. So the drift of the solar wind density illumination across the line of sight to the radio source causes the intensity scintillation. The scintillation time scale can be something like less than 100 millisecond to some tens of seconds. And then the shape of the density spectrum or density turbulence spectrum is related to the bulk velocity. Actually, we used this parameter to estimate the solar wind velocity from single station IPS at UT. IPS is most sensitive to radial flow coming out of the sun. So IPS, if you can measure interplanetary scintillation on several sources distributed in the heliosphere, one can probe several parts of the coronal mass ejection. Okay. For example, in the normally solar wind measurements are in situ sampling, but they can observe proper density, temperature and speed, composition and magnetic field. But in situ measurements are confined to near Earth orbit actually, and also they are in the ecliptic plane. So instrument measurements, they are point measurements as well as close to the Earth, nearly at about 1 AU, and they cannot provide three-dimensional view. They are confined to ecliptic plane. So Helios was the first spacecraft. This was this thing, late 70s, early 80s. This spacecraft went up to about 0.3 AU. That's one spacecraft. And then Ulysses was the first spacecraft probed the polar region of the sun at larger distance, actually. So Ulysses used Jupiter flyby, so it could probe something like 3 AU to great 5 AU solar wind, actually. So near Earth observations, and then because they are confined to ecliptic plane, they cannot provide three-dimensional view. And then recently the Parker solar probe and the solar orbiter, they are going to close to the sun, actually. So such missions, actually, some special missions like Ulysses, Parker solar probe, a solar orbiter, they are very expensive. They happen once in a while, actually. On routine basis, if we want to observe the heliosphere, or routine basis, if you want to study the interplanetary medium, I think interplanetary scintillation provides the interplanetary scintillation as well as some of the radio measurements. They provide the three-dimensional view, actually region inaccessible to spacecraft, and at all solar offset and all latitude, actually. And also large-scale long-term variation can be studied using IPS method. So for example, this plot shows the typical distribution of IPS sources observed at OT, actually. So this is the galactic latitude and longitude. This green line gives the path of the sun. Okay, with respect to the sun, we can observe large number of sources, actually. So this is just, and also all these sources, they have angular size less than something like 300 or 400 milliarcsecond. They are all compact radio sources. Some sources are very compact, actually. They are few milliarcsecond, actually. Yeah. Okay, so interplanetary scintillation, this radio source twinkling caused by turbulent solar wind. So this gives the typical geometry of interplanetary scintillation. With respect to the sun, okay, we can have line of sight going above the sun or below the sun, and east or west. So if you select the sources accordingly, one can get various heliospheric direction cut, actually. But the one important point we should have in mind is the interplanetary scintillations are line of sight integrated measurements. But the CN square along the line of sight varies as r to the power of -4, actually. It's a very steep gradient. So the most of the scattering is concentrated in the closest line of sight. So the most of the scattering comes from this region. For example, for this source, scattering comes from this region. So that gives some kind of positional confinement for IPS observations. Okay, so I'm not going very detailed in IPS, so just to give an introduction, I gave this. So IPS observation can be made using a single station as well as multi-station. For example, in a multi-station, as the scintillation pattern moves from one antenna to the other antenna, one can get the delay by correlating the IPS signal here and IPS signal at the next station. One can get the delay, but the IPS station, how far they should be away? They should be separated by at least the Fresnel radius. Fresnel radius is root lambda Z. For IPS, it can be something like 100 to 300 kilometers. So one need to maintain multi-station separated by hundreds of kilometers. So that can give the cross correlation. One can get the solar wind speed. But maintaining big antenna at 3 sides or 4 sides is very difficult, actually. So single station like UT radio telescope is very good because it has a very good sensitivity. One can get a good, for example, I've used the UT radio telescope. So you might have seen this picture in your lecture. And this is the Arecibo, this Arecibo diameter 305-meter diameter. This is 530-meter long and 30-meter wide. UT radio telescope operate at single frequency, 327 megahertz. Arecibo operates at 300 to 10 gigahertz range. So the resulting intensity scintillation can yield temporal power spectrum suitably model fitted or suitably calibrated to yield the solar wind speed, as well as the level of density turbulence, spatial spectrum of turbulence, and angular size of scintillating source. In olden days, interplanetary scintillation was used to study the angular structure or used to study detect or identify compact sources actually. So that's also possible with IPS actually. Okay. So this shows the typical dynamic spectrum. So this is the L band observation at Arecibo Observatory. The horizontal axis is the time in seconds. Okay, within 30 seconds, how the scintillation pattern varies. So the low frequency to high frequency as we go. So the scintillation pattern varies for a given scintille. So you can see, so here the scintillation pattern is thin compared to low frequency as well as the high frequency. So we see large variation from one scintille to other actually. Okay, so this is for 0 to 30 second of observation and 150 to 180. So we see, so the dynamic spectrum can give scale size and how do they vary as a function of frequency as well as a function of time. One can get idea about this. So, for example, Arecibo observations were very useful to get such important results. Actually, okay. So Arecibo as well as UT telescope, they yield a very high signal to noise ratio temporal spectrum. This is the temporal frequency by Fourier transforming the time series, one can get the temporal spectrum. This is the power. So one can fit and then get the solar wind speed, okay, at different distance from the, or different elongations from the sun. So, okay. Okay. So for example, this is the spatial spectrum of turbulence for ambient solar wind and then plasma associated with the CME, IPD plasma and ambient solar wind. So the IPD plasma spectrum is flatter than the ambient solar wind speed. So this gives the information. Actually, IPS can give information about not only about the solar wind and then the turbulence spectrum. For example, I'll skip this. Actually, this movie shows as we go. This is the solar offset. As we go close to the sun, how the density spectrum changes with respect to the source line of sight. Okay, source line of sight with respect to the sun. Actually, as we go very close to the sun, the spectrum becomes flat. So this has a lot of information about the turbulence produced in the solar wind. A lot of people are trying to understand the turbulence as a function of solar wind acceleration also, let's say. So for example, this gives the this thing magnetic field as a function of year and south pole to the north pole. So this is the year, this is the south pole of the sun to the north. Photospheric field actually. So they changes the polarity reversal takes place every 11 years, and then so the activity also goes from minimum activity to maximum activity. For example, UT IPS could give the density turbulence spectrum as a function of time and heliographic latitude. This image has been made not on the surface of the sun, not at the earth, not at the near earth environment, in between sun and earth distance at about something like 0.5 AU, how the solar wind is behaving actually. So you could see this minimum was a peculiar solar minimum actually. So the heliosphere was dominated by low density solar wind actually. This is the previous maximum. Actually. This maximum was not that strong compared to this maximum. So similarly, we could see the same trend in the near Earth sun also. This is near Earth sun. This is a LASCO brightness distribution at about 2.5 solar a day above the sun actually, which had a same pattern actually. Okay, so this is the solar wind speed as a function of year actually. Okay, south pole to north pole year. So the distribution of solar wind varies from one year to other, and also one cycle to another cycle, because we don't see a similar trend in solar wind distribution actually. Okay. So, for example, the evolution of coronal mass ejection can be tracked using IPS, but along with IPS, we use ground-based observation as well as space-based X-ray and UV images, coronagraph images, multi-frequency radio spectra as well as images are used, and in-situ observation. So this gives the image of the coronal mass ejection. Actually, this is before the advent of coronagraph. Actually, so LASCO coronagraph, we could image coronal mass ejection as it moving away from the sun. This is the 50 solar radii, 100 solar radii, 150, 200 solar radii away from the sun. As the actually this paper gave the evolution of the coronal mass ejection as a function of time actually. So we could track several mass ejection. I'm not going in detail. So this is the typical summary actually. So the horizontal axis gives the solar offset as we go away from sun to 1 AU, how the speed of a coronal mass ejection. For example, low speed mass ejection, they get accelerated, and some CME move with constant speed. And then the high speed CME, they get decelerated actually. Okay, one can see that actually. But this study gave an important clue that how these CME drag in the ambient solar wind affecting the CME evolutions actually. So this study gave a turning point for all the modelers to model the CME propagation actually. Okay, so for example, I will skip this actually. So I wanted to show this event actually. So this is an ejection observed in observed by Kenode spacecraft. This ejection was studied by LASCO. So LASCO observed a very fast CME, and then this was recorded in radio. So this is a UT Callisto spectrum, goes from high frequency to low frequency, something like 900 Mhz to something like 45 Mhz. So that gave a lot of information about the radio activity associated with the coronal mass ejection. And then we fixed the line of sight, and then we tracked the coronal mass ejection at two distances from the sun. And then we could get a very good estimate for the shock formation and then CME arrival at the Earth actually. So this is one example. So for example, at UT, since we could observe large number of lines of sight. This is each line is a line of sight, and again in one solar rotation, we get something like 30,000 lines of sight. So we can reconstruct. So UT could would give reconstructed heliosphere. This is 3 AU heliosphere. This is 3 AU diameter. And then this is the orbit of the Earth. This is the location of the Earth. So we could get the three-dimensional structure of the heliosphere. This flux row coming out of the sun can be seen actually. So the important point is the flux row expansion in the toroidal expansion as the poloidal expansion it's completely different actually. So this gave a, so radio observations actually, like radio observations of the sun and the interplanetary medium, and then remote sensing interplanetary medium using IPS can give a lot of information on the system. Okay, I'll skip these slides. Okay. So this gives a, sorry. I had one more movie to show you. Because this this thing, July 2012, there was a big mass ejection, but the mass ejection was moving away from the Earth actually. But it at Ooty we could image that mass ejection. This one is the in density, this is in speed, so we could get the mass. This mass ejection was the this mass ejection was the very high speed mass ejection. Okay, if it had hit the Earth, we could have had a severe geomagnetic effect actually. This one, actually. Yeah. Okay, so and also see the mass ejection rate as a function of year actually. So the mass ejection is the highest. For example, about 10 mass ejection per day we get during solar maximum. Okay, so recently we have observed the space weather effect on a pulsar also. For example, solar wind also can affect the dispersion measure of the pulsar. And I said interstellar medium, solar wind, and the Earth ionosphere. For example, this pulsar 2145 minus 07, DM was observed as a function of solar elongation. At one elongation, we had a large deviation from the average DM. So this large deviation was caused by a high-speed stream interacting with the coronal mass ejection, which caused a huge pressure pulse. This was a pressure pulse actually. So this pressure pulse caused a large deviation of dispersion measure. Okay, I'll stop here actually. So we have seen some aspects of solar radio observations and interplanetary scintillation measurements in understanding the space weather. Thank you very much. Yeah.
And thanks a lot, Manoharan. Thanks great for the introduction to space weather and interplanetary scintillation work. So we can take a few questions if there are. Any questions from the participants? No?
Can I ask a question in the meantime?
Oh, please. Why in the meantime?
Yeah. So this, in fact, the slide is right there. The pulsar observation that, it showed the increase in the DM. Was it accompanied by an intense change? Because this kind of plasma would do some interesting optics, right?
Yes.
If there was a sheet or a slab or a wedge created.
It was a huge pressure pulse actually. Yeah.
No, I understand. Did it do something to the pulsar intensity? It should do something to the pulsar intensity as well, because it's a significant, density.
You mean a reduction in pulsar intensity actually?
Yeah, like suppose it was a lens-like thing, you would have extreme scattering event. Okay, just as an example. Okay, to give you a sense of
that's right. Yeah, Desh, I agree on that, but we did not concentrate on that actually. But,
but if you were to look back now, it would be interesting to see how the intensity, because intensity, although you may not have great calibration day to day, you will actually find that there's a decent amount of calibration with respect to the system temperature.
Yes.
Right.
Yeah. Yes, I agree. Actually,
I would be curious to know what you see in the internet.
actually, whether this is the right forum to talk or not, but following this event, I identified more than 100 pressure pulse like this.
Right.
So we have to now we have to write a statistical paper on pulsar DM variation as a function. Yes, that's what
it's very relevant for all these timing guys, trying to
timing guys.
Waves.
Yeah, they are struggling with timing accuracy. Okay. Yes. Yes, Blesh, I agree with you. It's possible. Yes. Yes.
So that's one. And then there was a question, I forgot about something else earlier. This is about the speeds that you had and acceleration and deceleration that was seen for a variety of initial speeds, right? Closer to the
Earth, actually. Yeah.
It was very curious to see that regardless of what initial speed it began with, closer to the Earth.
Yeah, I see. Because of the drag applied by the ambient solar wind, it pulls all the because if the initial speed is very high, that CME decelerates very fast also. So apart from
I'm
this,
saying closer to the Earth, right? At the Earth's orbit, everything seems to converge to about 550 kilometers.
Yeah, that's true. Actually, this is a log scale, but you are correct actually, because they try to.
No, so it makes me wonder as if Earth is doing something. Earth magnetosphere is probably getting it to attain some, some locally compatible speed.
Individual CME actually, because this has been studied by large number of CME. Most of the CME they converge. Actually, most of the CME, something like 80%, 85%, they converge.
But don't you find that amazing?
Yeah.
Why should you know about the Earth distance?
Yes, that's true actually.
So the fact that we are observing it from the Earth has got to do something with it, or is it some intrinsic thing that on the scale of 1 AU something dramatic happens? Actually,
the drag force is directly proportional to the velocity difference square actually. Okay. For example, if the CME is V1 and speed and the ambient speed is V2, V1 minus V2 square, that is the drag force actually.
No. Okay. So is 550 kilometers per second is the ambient speed or not?
Ambient speed is something like 350 kilometer actually. Yeah, it's close to ambient speed actually. Yeah. Ambient solar wind speed, actually, you can see here. I find it amazing that things get accelerated.
Yeah,
it's amazing.
So make it come to 550 kilometers.
Okay, you can see here. This is the ambient speed at different along the equatorial plane, or typically along the ecliptic plane. This is the ambient speed. Actually, you can see that. Actually, it goes from 300 to something like 300 to 400 kilometer only. Yeah. This is the ambient speed. Yeah. No, that's true. That's true, Desh. Because previously people were using different, and also it gave another information. Internal energy of the CME. Sometimes they swim against the ambient solar wind. Actually. Some CME they get accelerated, but that's 1 in 1,000 or 1 in 2,000, something like that. Why they get accelerated? Actually, it's like a fish swimming against the current, actually, or again the ambient wind. So that's they give the internal energy or internal magnetic flux rope embedded in the CME. Okay, yeah, I did not go in detail, but that's the science now coming out also. Yeah. In the same paper, the evidence was shown actually how the internal energy of the CME can go against the ambient solar wind speed or ambient plasma. Yeah.
Yeah, I think we'll probably.
Yeah, thanks.
Yeah, I think what Desh just pointed out is quite remarkable, actually, given different situations that it ends up at 550 kilometers per second. But if there are no other questions, then we will close today.